NASA's mission to explore worlds beyond our own would never get off the ground without innovative ways to power all the operations that make that possible.
To explore the universe, you need a lot of energy.
Mike Houts is a nuclear research manager at Marshall Space Flight Center.
But one of the areas that NASA is looking at right now is fission. And so this is actually using the nuclear fission process to generate energy that can be used for any of our exploration needs.
Atoms are the most basic units of matter. The nucleus of an atom contains positively charged particles called protons. The number of protons in an atom determines the atomic number of an element. Elements are arranged on the periodic table according to their atomic number. Atoms of the same element have the same number of protons and electrons, but might have different number of neutrons. Atoms with different numbers of neutrons are called isotopes. Some elements have isotopes that are unstable. That is, they do not hold together well. When they break apart, they undergo a nuclear reaction and become radioactive. Two new elements are produced. The atomic number of these two elements adds up to the atomic number of the original element. Here's an example. Start with an atom of uranium. Its atomic number is 92. When this atom splits through nuclear fission, you get two new elements. One might be, say, barium, with an atomic number of 56. So what would the other one be? Do the math. Subtract the atomic number of barium, 56, from the atomic number of uranium, 92. You're left with 36. And that is the atomic number of krypton, the other element. When uranium splits, many elements can result, but the atomic number of the new elements will always be between 32 and 60, and the sum of their atomic numbers will always be 92, the atomic number of uranium. Okay, back to Mike Houts. He and his team are working to develop a viable energy source that would satisfy many needs of space exploration.
The applications, everything from the life support systems to in-situ resource utilization, some communication, really just all of the outpost activities is what they're looking at using the electricity for.
The system is based on old technology, the Stirling engine, which was originally developed in the 19th century. The engine converts heat into electricity. So, nuclear fission would create the heat that the Stirling engine would turn into usable electricity to power operations. This system is designed for about 40 kilowatts of power. That would power about 8 houses here on Earth. That's a little more than a solar array on the space station, which can produce 32 kilowatts. Plus, with the nuclear power plant, you don't need sunlight.
It's a very high power by NASA standards. It really gives us the opportunity to have a power-rich environment. It can also be operated anywhere on the surface of the moon, anywhere on the surface of Mars. So it gives us a lot of flexibility, a lot of power capability. But as reactors go, it's actually very, very tiny. Compared to a terrestrial reactor, it's about 1/20,000th the power level.
And the safety concerns associated with nuclear power are virtually non-existent with this system.
They have what's called a negative temperature reactivity feedback coefficient. What that basically means is if the reactor starts to warm up, the system itself actually gets less reactive, and that'll tend to cool the system down. If the system starts to cool down too much, the system will actually shrink and become slightly more reactive. That'll cause it to heat back up. So the systems themselves are very stable.
And any fears about the nuclear material creating a disaster in the event of a launch mishap would be erased thanks to good engineering.
The nice point about reactors is they operate basically by having the right materials get in the right geometry, and that will cause the reactor to turn on. And so what's been done in the system is to basically make sure it only turns on when you want it to turn on. And the system is designed such that during launch, any credible launch accident, that it will not inadvertently turn on.
So, very safe and incredibly efficient.
The amount of fuel we have on board, we burn about 1% of our fuel every 12 years. And so we're not going to run out of fuel. However, there'll be other parts of the system that might limit the lifetime.
The prototype system doesn't use nuclear fission. That's for a future iteration of the concept. For now, it uses resistance heaters that closely mimic the heat from fission. The Stirling engine turns that heat into electricity. Here's how it works.
What that simulator does is it heats the coolant. In this case, we're using coolant. It's a mixture of sodium and potassium. Heats that coolant to about 850 Kelvin, and then that hot coolant is used to provide power to a Stirling power conversion subsystem. What that does is it takes a portion of the energy that's in the NAC coolant and converts it into electricity. About 25% of that energy is converted from heat into electricity. Now, in the process of that energy being transferred to the Stirling engine, it actually cools the NAC down, and so that slightly cooler NAC then goes through the circuit. It's repressurized in a pump and goes back through the core stimulator where it's heated back up and then continues in the circuit.
NASA scientists, working with the Department of Energy, think that they could have a nuclear fission-based version of this system in place within 5 to 6 years.
When it comes to space exploration, we humans have always taken the supplies we need to survive. Water, oxygen. We had to bring it to the moon and to space stations we've occupied. This has worked because we haven't strayed too far for too long. But now, NASA is returning to the moon, and this time to stay. So finding and using lunar resources is imperative. NASA calls this in situ resource utilization, ISRU for short. And it's a big part of NASA's plans for establishing human outposts on the moon and eventually Mars. But looking at the surface of the moon, it doesn't really look like there's much to work with. No plants, no animals, no obvious water, just a lot of dust and rocks. But it turns out, that's the key. In the lunar soil or regolith, there are enough chemical elements to make lots of the resources a colony like this would need. But how do we take moon dirt and get oxygen out of it? Well, recently on Mauna Kea volcano, on the big island of Hawaii, ISRU scientists and engineers took a big step towards solving that problem. There, they tested 2 reactors that can convert the seemingly sterile gray dirt into usable oxygen. Excavating rovers dig up the regolith and deliver it to the reactors. That's when things really start to heat up.
We get the material to the reactor, and then we do the chemical reaction and store the oxygen.
Tom Simon is the ISRU Project Office Chief Engineer.
In terms of the chemical processing plant, heat passes over the heated regolith. That's when the reduction takes place. And from that point on, it's mostly cleaning up the water, electrolyzing the water, and then cleaning up the product oxygen.
And surprisingly, it doesn't take a whole lot of digging to provide a pretty healthy amount of very valuable substances.
What we're shooting for is about 1% of the mass of the soil.
Larry Clark is the ISRU Program Manager for Lockheed Martin, one of NASA's partners in this project.
So in this case, we're taking about a 12-kilogram load to make about 120 grams of water. Depending on where we get the soil on the moon, we could get up to 4 times that amount. Conservatively speaking, we've been shooting for 1% reduction. And that's really our bare minimum.
While the machines are busy providing resources, the astronauts will be free to do what astronauts are supposed to do: explore and make discoveries.
On the moon, we would set up a depot, whether it's the fuel cells coming to get oxygen, whether it's the crew coming to get water and oxygen, whether it's the propulsion community coming to get oxygen for propulsion. We would store it in our depot, and they would come and get it periodically. For this particular setup, we have a cryogenic oxygen tank here. That tank stores about 8 hours worth of oxygen that we would make. So imagine if we did that 6,000 hours a year, how much oxygen that would be.
We can drink the water, we can breathe the oxygen we make, and we can use it to fuel cell vehicles. Eventually we can get up to a production rate where we can power the ascent vehicle, we could power launchers. Perhaps we could even power hoppers that would take you from place to place on the moon. So there's lots of different things we can do.
NASA sent 2 prototype reactors to test 2 different systems. One of the systems, called Pilot, is designed to sit on top of a robotic lander, meaning it could be launched before sending a crew to the moon, touch down on the lunar surface, and begin to produce oxygen without the need of a human being. The other prototype system, known as Roxygen, is a larger-scale system that might require astronauts to set it up. Both reactors worked well in Hawaii, making researchers optimistic that this approach will be successful on the moon. Scientists and engineers are going over the data from the Hawaii test now, trying to optimize the design to create the best system. More testing and revisions lie ahead. So, like the adventures of old, a new generation of pioneers will soon leave the familiar surroundings of Earth. And today, The scientists and engineers involved in the ISRU program are hard at work inventing the tools that these explorers will use as they venture out to establish the first human outposts on other worlds.